Okay, I'm back, and now we want to start talking about different classes of minerals. And the first class of minerals is going to be the silicate minerals. So most of the minerals on the surface of the earth and inside the earth are silicate minerals. So what are they composed of? Silicates. So what do we mean? Sila means silicon. So that's going to be the black one in that picture there. And so let's look at the property of silicon and the property of oxygen on the periodic table. So if you recall, silicon is in column number 4. So what does that mean? How many valence electrons does silicon have? Okay, it's going to have 4. So it's, now you can think of those 4 electrons that silicon has as being like hooks. And each one of those electrons has the ability to hook onto a different atom. Now we said that the two most important elements in the crust were silicon and oxygen. So what happens is that the silicon grabs onto 4 oxygens, and that's going to make a silica tetrahedron. All right, so let's put a silicon in the middle, and let's attach 2 oxygens to it. Now, remember that the electrons, they don't like each other because they're the same electrical charge. Like charges repel. So if you had 2 electrons, where would you put them so that they were as far away from each other as possible? Okay, you'd put one of them over here, and then you'd put another one over here. So they're as far away from each other as possible. Now, what would you do if you had 3? What would they want to do? Well, you'd have one here, and you'd have one here, you'd have one here, so it'd make a triangle. Okay, now let's say that you've got 4 electrons. Where would they go? And you'd say, oh, well, they're going to make a square like that. No, they're not, because you're thinking 2-dimensionally. So any of you ever see the Star Trek movie Wrath of Khan, and they defeated him because he was thinking 2-dimensionally instead of 3-dimensionally. It's a wonderful movie, so you need to watch that movie. But anyway, so getting back to this, we've got 4 electrons that need to be as far away from each other as possible, and what's going to happen is they're going to make kind of like a pyramid, so that you're going to have one of them will be here, and another one will be here, and then you'll have a third one. It's kind of hard to draw it, but the third one would be behind the silicon, and then you'd have one on top. So that you would end up with something that would look like this. So the silicon's in the middle, and then it's got these 4 oxygens, and notice that those oxygens are as far away from each other as possible. So tetra means 4. So this is the silica tetrahedron. And so this is the basic building block of the silicate minerals. Okay, so now this is getting kind of technical, so just bear with me here. Let's look at the electrical charge of this thing right here. So you'll notice that the oxygens are in column 6 of the periodic table. So they want to take 2 electrons. So each one of these would be a -2 if they were ionized. Now the carbon, on the other hand, is a 4. It's a +4. So that when you add +4 and -8, you end up with a -4. So that's the charge on this thing. So if you had another, so let me Here's another one. What do you think would happen if you tried to take these two silica tetrahedrons and make a mineral out of them? It wouldn't work because they would be repelled by each other. So one way of holding them together would be to put something positive in between them. So this one's negative, but if we put another atom in between that's positive, then the positive would attract this one, and the positive would attract this one, and it would hold that thing together. And that's exactly what nature does. So for example, let's look at olivine. So olivine has these silica tetrahedrons, and do you notice what other elements are in olivine? It's got magnesium, and then it's got some iron in there. And if we go back to this previous slide, find magnesium and find iron, and do you notice that they have plus charges on them? And so they kind of act like a glue that holds these things together to make the mineral olivine. Okay? Now you don't need to know how this works, but I'm just showing you that you can glue these silica tetrahedrons together this way. Now let's try a different way of putting them together. So what would happen, here's our two silica tetrahedrons, if I take off the oxygen on this one and I attach it to the oxygen on this one. So now notice that the two are sharing an oxygen in between them. That's another kind of mineral. So if you look at this chart here, it shows that you can take these minerals and you can make a chain out of them, and that's a particular kind of mineral. Now you can go one step beyond this, because could you imagine that I could remove this oxygen and I could remove this oxygen and then attach it to another chain, and then I end up with a double chain of them. That's another kind of mineral. And then can you imagine that I could remove, let's say I remove this oxygen and this oxygen, and then I take another chain and I glue it to that. Now I've just made a sheet mineral such as muscovite. So your micas. And then finally, the most complicated of all would be what would happen if every silicon was attached to an oxygen, and then every oxygen was attached to a different silicon. That would make a three-dimensional structure such as quartz. So I just want you to show you that the silica tetrahedron is very important because it makes up 90% of the rocks found in the crust of the earth. So it's a very important set of minerals. All right, let's take a break, and when we come back, we'll talk about other classes of minerals.